Today's presentation is going to be given by Daniel, who's the principal scientist in the red cell team under me in the lab in London. And he's going to give you a lecture about the fundamentals, so the basics of electrophoresis, alkaline electrophoresis, and high performance liquid chromatography. This has been, as you know, this meeting has been held on Zoom, and we will share the Zoom link via the BSH cloud. The last lecture, I shared a link to Dr. Sahar and Victor to, if you could download the lecture in Zambia and share it amongst yourselves, please, rather than me sharing access to my personal Google Drive, which I don't want to do. So all the people that are asking me for access, I'm not going to accept that.
It was too big. It was failing to download.
Okay. Well, we might have to look at another way. I'll see if I can find another way to get it shared. Okay. All right, Daniel, do you want to go ahead?
I can indeed, if everybody is ready. So good afternoon, at least here in London. I hope everyone is okay. Yes, thank you for the invite, especially Yvonne and this initiative. It's not every day that I'm doing to go through the fundamentals. On this case, electrophoresis and HPLC. So it's a theme that we teach many times because we are part of a teaching hospital. So therefore, we teach these principles to from students to technical staff such as ourselves, scientists and medical as well. So as Yvonne was saying, we're going through a little bit through the basics, but we'll touch base actually how those basic principles are applied to everyday techniques used even today. And also touching points in which advantages and especially the limitations that I have into the theme that we're working toward, which is hemoglobinopathies. So we're going step by step to see how these techniques have been used currently, how they can be improved, what's in the pipeline, which will also be used in the future perspectives as well. And that will be specifically, I'm talking about electrophoresis, but that will be, we're touching by just an alkaline electrophoresis, which is one of the most used for protein separation, in this case, hemoglobins. So we're going through the principle and the same thing for HPLC, but it will be interesting to see how the results also will show and how those will be interpreted to reach a certain conclusion as well. I would like to, because I'm sharing the screen, I cannot really see who's attending the presentation. If you have any queries, especially when we get to the point of the cases, we've seen time and time again that is much more efficiently, and the retention of the information I'm providing to you is much better if you just interrupt me. I don't mind. So if you interrupt me as I go along, if you have any questions, or if you want me to go through a certain principle yet again, it's all about the repetition that the training is based. So do please interrupt me as I go along. So we'll start with the alkaline electrophoresis principle, basic principle. Remember that electrophoresis per se is really used. The core idea is that we want to separate molecules in a certain solution. All of that separation is going to be pretty much based upon their total electrical charge. So you can already see how that is going to be applied. You need to apply a current into a certain matrix. A matrix could be either gel, which could be commercially available, or you could even do it yourself as long as it has the right consistency. And there is various protocols out there and kits that you could do your own gels. What could be cellulose acetate as well. It's been used much commercially, especially on some platforms that are semi-automated, which we're going to see in a minute as well. But the basic principle of electrophoresis is that you have a positive electrophoresis, which is the acid, and then cathode, which is like a negative pole. The point of origin, basically when you apply your sample, when the molecules are present, they're going to be separate depending on their charge. So when the electrical current is applied, if the molecules are positively charged, they're not going to progress very much towards the positive pole. But though the negative charge protein is going to be moving slowly towards the charge, which is the opposite. And to move along, it's important to remember other methods, other electrophoresis. We're looking at alkaline, but also you have the acid. So yet again, I'm just focusing on the alkaline because the acid will have slightly differences as well. When the hemoglobin itself, when is paired for this technique, it acquires a negatively charged. So the whole molecule overall will have, and this is normal hemoglobins, will have a more negatively charged. So you can already foresee what's going to happen. It's going to progress towards the shell more efficiently. Other ones are more or less positive charged. So hemoglobins, we're talking as a loose term, really, but there is various hemoglobins as well. And it's important to remember that each hemoglobin will have its subunits or peptides which made it up. So we know that adult hemoglobin is based within beta chains and alpha chains. Again, the overall charge of the hemoglobin A will be quite negative. So it's going to progress quite nicely towards the end of the matrix of the gel. So you can see that band, and I'm going to show you some results, how easy that is going to interpret as well. But within the realm of hemoglobin, it's not just hemoglobin A that you have. You're also going to have hemoglobin F or fetal. So, hemoglobin, as you know, has different subunits that made it up. So fetal hemoglobin is built on gamma chains and alpha chains. The common ground of all hemoglobins are always going to be alpha chains. So the distinguishing factor of how much is going to progress is actually what the beta component is going to be. So fetal doesn't have beta chains, going to have gamma chains. So it's going to progress a little bit less towards the gel because it's not as negatively charged as the hemoglobin A. So you can see that quite nicely. But that always sets the ground, doesn't it? Because if you're going to have changes in the peptides, and electrophoresis has been around for a really long time, is almost getting to a century, which electrophoresis has been firstly described in literature and be able to separate hemoglobins. So, but you can see how it's going to be producing consistent results because his electrophoretic mobility is going to be pretty much standardized if the whole protocol has been followed as it should, and the current is constant depending on what protocol you'll be using as well. So you're going to see a pattern, which is quite nice. It's nice, especially when you're training someone or you want to make a systematic approach in diagnosis. You're going always to see that that pattern is going to be quite important for you to have a consistent reporting strategy as well. Getting to a stage where also more variants are going to appear. Quite interesting. So we know that hemoglobin S, which is quite common, we know that is going to create a hydrophobic valine residue. If that hydrophobic is going to mean that just that little acid means that the whole molecules are going to be polarizing because they're going to be sticking together. It's really low frequency in the red cell, which pushes it and creates the typical S-shaped. Hemoglobin S itself, because it has a change, it has a change of that amino group, which will change the total overall charge of the hemoglobin itself, hemoglobin S. Yet again, the electrophoretic mobility is going to be different and is quite nicely distinguished between F and A. So you're going to see that runs before F and A.
Me, Daniel, I thought it might have been just me, but it's not just me. Every time you play the video, you break up and we can't hear you very well. So I think you might have to play the video and talk separately.
Okay.
Yeah.
Let me see if the settings are all okay. It seems my connectivity is working okay. So just the video. which is almost on the end anyway. But you want to show me if you're breaking up as I go.
Yeah, you're breaking up now. So I thought it might have just been me, but Catherine's texted me. She's got the same problem.
Fine. So you can hear me okay now because I've stopped the video, I guess.
Yeah,
Yes?
yeah.
Amazing.
Yeah.
So I'll stop as I go. Thank you. Thank you for letting me know. So hemoglobin C disease, which again is a mutation that's in the amino acid basis, where you came from a glutamic acid negatively charged hemoglobin A that moves so much towards the end of the gel, it has a lysine, which is quite more positively charged. Being positively charged, you can already see it's not going to progress much in the gel, and therefore it's going to be just before the S. As a comparison, for comparison purposes, if you have a patient or someone that has an SC disease, you're going to have the two bands present quite nicely distinguished between them. So if you have that systematic running electrophoretic mobility, you're able to put that into contrast and run various samples. And as long as you have, and this is quite important, that you have a control. Controls not only give reassurance that the technique actually has worked, is also going to work almost as a ruler as such, especially now in electrophoresis, because you were able to see how much progression has happened on the control, which you know what is in it, and you can use that for comparison purposes as well between the samples that you have. It is not uncommon that that control might be run multiple times depending on your size of the gel. Sometimes gels are quite limited in how many samples you can run within a gel, especially the ones commercially available. But if you made your own gels, depending on how many wells you have created on your own gel, this might be a good idea to insert controls maybe in the beginning, middle, and the end, or just two of them in the beginning and the end, because it's quite nice to have that ruler as much. So to give you assurance that all the bands are running where they should. So this is just an example, again, just looking at alkaline electrophoresis at pH of around 8.4, which is usually the standard for alkaline electrophoresis for hemoglobins. You can see that if you have a normal patient, it's going to have all hemoglobin content just running within A. Sometimes you will be able to see hemoglobin A2 a bit more faint, but it's detectable there. And that patient is going to be, if you look quite here towards the end. And obviously, if you have the bulk of your hemoglobins is going to be just hemoglobin A, the bands are also going to be much thicker and present, as you can see here on the first line. In newborns, it's not different, depending on how much proportion, and it depends if the patient is prem or what is this gestational age when the baby was born. You will see, depending on the proportion between F and A, also the thickness and the intensity of the bands are going to reflect that. So in this case, you can see that you have more hemoglobin F than hemoglobin A because of the thickness. There's ways that you can use to extrapolate that to a measurement, although as we moved along and more technologies have appeared, it's not really recommended to use a gel electrophoresis, even if coupled with another ways to measure the intensity of the bands as to give a percentage results. In a sickle cell disease, as we saw before, you're going to have just one band running in the SEP position. In a sickle cell carrier, I'll try you have two bands as well. SE disease, similarly as well, you're going to have two bands, but this time obviously running on the S and the C position, and your control, which is always necessary to run within your technique. Advantages and limitations of it. As I said, electrophoresis has been around for almost a century. From 1937, I think it was first described. So his usage has been throughout a lot of techniques. So obviously being used for hemoglobins as well, but you need to remember that it's quite a simplified setup, as I described before. As long as you have a matrix, and as long as you have all the remaining equipment, which is not expensive or difficult to go by, and you have a power source which the electrical current is going to apply, the molecules of hemoglobin is going to separate quite nicely. So its setup, its procedure is not difficult. And as we saw many times now, they're more or less to make an accurate diagnosis. However, its simplicity comes with obviously some limitations as well. It's quite manual, depending on the amount of samples you need to process, and they need to be batched together, so you will be able to process them in a timely manner. Might be complicated. And being a manual process is not difficult to go to manual processing errors as well, mispipetting in the wrong well as well. So that is a disadvantage of relying on such a technique as well. It can be time consuming. Obviously, being a manual process, you need to prepare one patient at a time to be dispensing and then running it and then to read the gel. It might take a while for if you have a lot of samples to process. So therefore, that's something that needs to be taken into account when looking into this technique as a way to separate the hemoglobins. Definitely these days is very important to measure the hemoglobin A2 for beta thalassemia diagnosis. And this technique, as I said before, even if coupled with other ways to measure the intensity of the bands, is not a reliable way to give an accurate estimation of how much the hemoglobin A2 will be. Definitely not for diagnostic purposes. Being, again, a more simplistic technique, and because the runtime is not that big as well, there is more than 1,300 hemoglobin variants described. Obviously, some will be more prevalent in one areas than the others, but they will, or they might have, quite similar gel mobility or electrophoretic separations. So some of them might even run within hemoglobin A2. So it's not going to be as reliable for a lot of hemoglobin variants. That is specifically the case, and possibly one of the biggest limitations when you use hemoglobin electrophoresis, possibly as your first line screening test as well, that you can see that within the same position, you have hemoglobin A2, hemoglobin C, hemoglobin E, and hemoglobin O running all in the same position, which might be very tricky first for you to see if there is a variance and possibly, other comorbidities running on the same position. Even more so when you have on the side hemoglobin S, D, and G running as well in the same position. We have been involved, or we heard about and we investigated a couple of incidents that happened in the past, which, for example, G Philadelphia, which is the most common alpha chain variant present in Africa, has been misdiagnosed as a sickle cell carrier simply because both bands run on the same position. So it's quite important to know those limitations and possibly have a secondary line of tests, which you could bypass the possibility of misdiagnosing hemoglobin variants that you're detecting in alkaline electrophoresis. Times have progressed, and even being a more simplistic technique, it can be coupled to a more automated way, and its sensitivity can be increased if you used, you basically put it into an analyzer. So there is I call it a semi-automated electrophoresis, because there's still a manual component which you need to be participating in, so you will be able to use this. And this is the example of an analyzer from Hemex Health called the Gazelle. It's been used in a couple of settings. Thankfully, we were quite fortunate that Hemex Health, about in 2022, if I'm not mistaken, approached us because they wanted to do a little validation with us. So they provided the analyzer and reagents, and we were basically running, we will test the limits of its usage and capabilities. So we did run quite a good amount of samples, which I'm going to present you the results soon. But yet again, it's nice. It's devised as a point of care, is battery operated, so therefore it can be taken to the community to process this. So therefore, it's much more designed for a point of care setting. In principle, yeah, it's quite interesting the way that it was applied to the analyzer itself. You can see this little cassette with chip based, and you have a cellulose acetate band here. So this is where the hemoglobin separation is going to happen. Being semi-automated, there is still a component that you need to do it manually, which is pipetting the sample, the buffer, so the anode and the cathode can work, and there is timings into it as well, which timings we notice that is something quite critical as well. And the analyzer itself is set up with a timer, which is a nice addition. It will give you, once you pipette it a stage, it will start a countdown for you to be able to carry on the procedure, minimizing the errors or being able not to add the reagent where you should. The measurement is quite simple as well. It has two ways to read it on a white light, which you'll be able to see visually the bands running, which gives you reassurance the assay actually is working. And then on a 409 nanometer illumination for the quantification purpose as well. It has been integrated in a patent algorithm within the analyzer that, looking at the intensity of bands, it gives you a provisional result, which is the one down here. You will look intensity of the band, giving you a percentage of how much that will be. It will also give you a likely diagnosis, which obviously needs to be taken with a pinch of salt, and you need to interpret it in the context of all other information that you might have about the patient that you're looking or taking after. These are a couple of results that we extracted from our validation data for HEMEX. So you can see how it looks visually. This is actually the band you look on the analyzer when it's running, but it gives you these results as well. So do remember that in the majority, this is a normal sample that we just run, and you just use the majority of hemoglobin was hemoglobin A. Depending on how much it has detected A2, it is giving a provisional or suggested diagnosis, saying that is likely beta thalassemia, but that really depends on other factors which need to be taken into account, like the sample age, which we tested to see how reliable it was within the manufacturer's specifications, how long the sample will be stable for to use this analyzer. Various other phenotypes which we tested. A sickle cell carrier actually showed good result, where the majority of was detected alongside with the S, giving again a likely sickle cell trait diagnosis. I think I need to emphasize that even if this is a point of care setting, it is strongly recommended in the BSH guidelines that a secondary method is always used to confirm your first screening results. So even if this result was giving as a result as a sickle cell carrier, it could be coupled quite easily, something that could even be used in the community as well with a sickle solubility test. Having these two together will be quite more beneficial and minimize the amount of errors. In this case, we had S, F, and A. So if I recall correctly, this result was a sickle beta plus patients. So we wanted to see how much of separation it was giving, but also how much the quantification was on it. To remember that in this case, it didn't even detect the hemoglobin A2. On the sickle cell disease homozygous S, it was just a normal, nice, concrete band, which gives you the majority of it was hemoglobin S. So there's a couple of results that we extracted from the validation data, but something that we also needed to feed back to the manufacturer that obviously just an analyzer, even point of care, doesn't substitute the need for you to look at the whole information that you might have. For instance, being just an analyzer running electrophoretically the bands to a certain point and then be measured, you will not be able to tell if the patient was transfused. So it will call a likely sickle cell trait in all transfused hemoglobin S as long as the S was around the range looked at the sickle cell carrier level. G Philadelphia, as I said in the beginning, as a limitation for electrophoresis, alkaline electrophoresis itself, it will, the G's, the D's, the Auschwitz-Christiansborg as well, will all run in the same position, will all run on the S position. So therefore, it could give the likelihood of being a sickle cell carrier, but it could be just as a G Philadelphia as well. And that's something quite limiting because the significance of both is quite different as well. The detection limit was something that we quite were interested to test. So therefore, we did various combinations. But we, for instance, we put through these analyzer transfused SC disease, where the SC post-transfusion was around 8%, and you didn't detect any. But if you looked, and some work has been done towards it as well, but there is the detection limit or that the analyzer and manufacturer discloses. So something we need to be careful if that is even considered to be used as a post-transfusion setting. So again, very things we need to take into account if we decide to use this analyzer. Now, going to the HPLC, I'm afraid that I need to run the video for a bit and then talk, as I was planning to talk over it. So the HPLC, just going through the basics again, high performance liquid chromatography. If we start with the second part of the HPLC, the liquid chromatography is always based in two phases, the mobile phase and the stationary phase. When we reach the point that we're going to inject the sample, we're not injecting pure hemoglobin or an extract of hemoglobin. So we're injecting into the analyzer automatically or manual blood, whole blood. So obviously we're talking about hundreds of molecules, and we are just interested in one molecule, which is inside the red cell. So we need to get access to it. So when the sample is injected, various things are going to happen to the sample itself. But essentially, we are just going to focus and target the hemoglobin. Everything else inside the whole blood is just going to be discarded. The mobile phase is not just used, as the name says, to make the sample or the molecules of interest mobile to the stationary phase. It also can be used to alter or make the hemoglobin of interest, in this case, hemoglobin, even more targetable, if I could add that term. When hemoglobin is within the contact of the mobile phase of our analyzers, it acquires a net positive charge. So now that we talked about the mobile phase, the stationary phase, HPLC is being used for many molecules, not just hemoglobin. It could be used for molecules quite much more small than hemoglobin itself. It all depends on how it is constituted, what is within the cartridge, the column, the stationary phase, all terms explaining the same thing. Is a little bit of metal piece, which inside there is some kind of resin or polymer that will be able to target and capture, and that's quite important, capture the molecule of interest. Depending on what molecule you're targeting, you will be able to use different type of columns. When HPLC is also coupled in other techniques, for instance, mass spectrometry. If you're looking into a molecule that you desire to target and measure via mass spectrometry, it's not uncommon to couple HPLC to the mass spec. So you'll be able to, yet again, target the molecule itself, getting rid of all the interferences, then it will be injected into the following analyzer, in this case, the mass spectrometry. For hemoglobins itself, you don't need that setup. HPLC will be sufficient because of the molecule itself and its properties, but it really depends on what the stationary phase, the column is made of. So you can see that smaller particles that are compacting the column is going to be more efficient because it's just going to be it's going to be targeting it better. It's going to retain it better to again be eluted. Bigger particles means that it's going to be less efficient because many more molecules will be there, and then you need to target it differently. So as I said, on the bio-rad analyzer, the hemoglobin, when in contact with the mobile phase, acquires a net positive charge. And the stationary phase, quite conveniently, is negatively charged. So therefore, if the hemoglobin has a net positive charge, it's going to be automatically captured by the negatively charged resin or cation exchange resin that is within the column. That is the way that you targeted solely one molecule out of the hundreds in your sample. Everything else gets extracted or discarded. And then when you have everything together, when you have all hemoglobins captured, you need to do an elution phase. That elution is created automatically while the analyzer and is going very precisely high, hence the name high performance, because it's very precisely is going to incrementally increase that elution buffer to systematically detach the hemoglobins out of the stationary phase, and one by one is going to be measured. Being the basic principle of being captured by its charge, you can understand that hemoglobins that have fewer positively charged is going to be eluted faster. When a more positively charged hemoglobin, it needs a higher concentration of the elution buffer to actually get it out of the column. What you get on the end of it, a beautiful HPLC plot, which has, on the beginning, it will give you basically the audit trail of which is the name, if you have given one, especially the serial number of the analyzer. Quite handful if you have more than one. We have 4 in our laboratory, so we need to know exactly where the result came from. In the next section, you're going to see the patient identifiable data and some audit trail when the sample went through the analyzer, when it was processed, if the result was generated or printed like this one. So also going to detail here on the analysis data section. So you have that audit trail present as well. The next is the peak table with the percentage results. So you're going to see that there's multiple columns, but in essence, it's just going to be the second and the third column. The meaning of it, why is they separated, is because the second column gives you the calibrated peaks that we need to calibrate ever so often, and the rest is just to be quantified on the third column. It has some provisionally given names, but always needs to be taken into account that hemoglobins can run in the same position as known fractions that the analyzer gives. So we need to take that into account if you're looking at a more complex result. And the chromatography itself, the table itself with the values is not sufficient to give an informed decision. We need to look at the chromatography itself to see if it was successful, but actually visually you'll be able to detect some peaks that in conjunction with the whole result, it could be meaningful for us for interpretation. Advantages being an automated process, great. It's not as a gel electrophoresis, you prepare one sample at a time. You could just load, as the analyzer is showing, the picture is showing, various samples. You could put the QC, the calibrators, and you just run at everything automatically. Being as a principle in HPLC is going to have a better separation of the hemoglobins, as even though the chromatography showed and the peak table, you will be able to measure other hemoglobins and separate much more accurately as compared to the gel electrophoresis. And especially the quantification is a nice IVD-CE marked analyzer, also has a FDA approval to be commercialized, and the quantifications are good. Obviously, you have calibration process, and QC also needs to be in place just to make sure that the percentages that are coming out are accurate. Also giving you the second picture is another HPLC analyzer which we have in our laboratory, which is the Trinity Biotech by Resolution. So it is very similar in many ways. It's just the separation might be even so more better in a way, because while each sample takes 6 minutes to run on the BioRad analyzer, on the Trinity analyzer, you have a mode, you can expand the separation of hemoglobins by 8 minutes. More time, more separation, more reliable chromatography. It means that you will be able to detect some hemoglobin variants that might be ever so coeluting with A. So it is useful in various times. It also provides a measurement of hemoglobin A2 when there is presence, for instance, of hemoglobin E. So in BioRad, analyzer doesn't, because hemoglobin E runs exactly in the same position as hemoglobin A2, so therefore it's not going to give you an A2 measurement. Being automated, being commercial, being through all of those bonuses has a price tag. So the equipment itself needs to be purchased or on a reagent rental basis, but you need that. You need to keep it, you need the reagents, and you need the QC material that comes with it, so you have a reliable system and diagnostic service as well. It's not just having the analyzer, you also need to put it in a place where it actually is going to work properly. The HPLC is temperature sensitive. Although there's ways that the manufacturer tried to go around to make it less temperature liable, it is very important that it has nice facilities with a controlled temperature. Otherwise, the chromatography is going to run faster or slower depending on the temperature you're having. It gives you a lot of data, but the chromatography actually needs to be looked at quite carefully, and that is acquired over time, over experience. So it is required that when looking at the chromatography, especially even on our settings, when we have a new scientist being trained, we go through a rigorous period of training, because it takes a while to understand chromatography, the results itself, and especially picking up the little details that actually have quite big significance. As just showing a couple of examples, and I'm simplifying the report, just extracting the information that is necessary. For instance, if and being a hemoglobinopathy screening, also needs to have some kind of hemoglobin separation technique with quantification of the hemoglobins, but also a full blood count. You need to have both inside them, so you'll be able to diagnose the hemoglobin status of the patient fully. On this case, just as an example, this is how a sickle cell carrier will look like. It will not invalidate the need of a secondary line of test, such as a sickle cell ability test. If it's positive, like the picture is showing, the diagnosis of a sickle cell carrier and the red cell indices are in keeping with it, that is easy and straightforward. On another setting, or in a clinical basis, if you have an SC disease, this is how the result is going to look like. The S and C are quite well separated, quantified, the hemoglobin A2 is also there, and the full blood count in this case was slightly microcytic hypochromic, but it could be iron deficiency or alpha thalassemia in play. Sickle cell ability is enough to confirm the presence of hemoglobin S, but it's not enough to confirm the presence of the other hemoglobin variant you have detected. On this case, hemoglobin C. You could use another technique, such as the gel electrophoresis, alkaline will be sufficient, IEF, or mass spectrometry, depending on what the settings you have. It needs to be a different principle as your screening method, so it cannot be used HPLC as well. As an example, as to prove the point that the chromatography needs to be looked at quite carefully, I usually ask the audience, in this case, which are the differences that you can see. So if you feel that you know the answer, do please comment. But for the sake of time and the presentation time that I've been granted, these are two samples, two different ones, and the significance of both are quite different. Both of them are antenatal screening samples, so the patients were pregnant, so they're being screened to assess the risk for the baby developing a serious hemoglobinopathy. So if I say that the result on my right is going to be a sickle cell carrier result, which the variant was around 31%, is in keeping. I'm not providing the full blood count results in purpose, but that will be a sickle cell carrier. If you look at the plot on the left, you will be able to see a couple of differences. The quantity is not one of them. Usually it's said that beta chain variants will give around the percentage around 40, 35 to 40, but it's not taking into account if the patient is iron deficiency, iron deficient or has alpha thalassemia. So all of that needs to be taken into account. But there is a little detail in the plot on the left, which is an unknown peak of just 1.5%, which instantly should pull you to think about a different kind of hemoglobin variant. In this case, it was the G Philadelphia. As I said, is the most common hemoglobin variant present in Africa, so therefore quite common for us to see here, even in London. And that's all for me. Thank you very much.